So now we come to Hilbert basis theorem. So if a ring R is Noetherian, that would imply that the polynomial ring Rx is also Noetherian. So immediately we can see the corollary. So Rx1 to xn, you are attaching this n indeterminates to the ring R. This is same as first attaching n minus 1 and then attaching this xn. So you can build these rings inductively. So this is also Noetherian by induction. So having n determinates is also Noetherian by induction, because inductively you can keep on adding elements to build this ring. So first add x1, then add x2, and so on. Just this procedure. Now since ideals are finitely generated in this ring, because we have just said that this is Noetherian, so they are also finitely generated in if you modulo out an ideal I from this ring, precisely because the ideals here which contain I will descend here. They are finitely generated here, they are going to be finitely generated here also. So finitely generated algebra over a Noetherian ring is Noetherian, because this is the definition of a finitely generated algebra. Now fields are trivially Noetherian, and therefore the ring of this form kx1 to xn modulo I is also Noetherian. Now if you have seen algebraic geometry, you can immediately realize that this is the coordinate ring. So this is the coordinate ring of any variety. So say a function f equals to 0 in a plane or in some kx1 to xn, this will generate this ideal I. So you modulo it out, you get the coordinate ring corresponding to this function or to a set of polynomials which will generate this ideal I. So this is also Noetherian. So now you can see that how algebraic varieties which arise from such coordinate rings are essentially Noetherian schemes. So let us now come to the proof. So we have to show that if R is Noetherian, that would imply that this polynomial ring, if you adjoin this indeterminate x to R, is also Noetherian. Now first look at the elements of this polynomial ring. So they are just polynomials of this form fi. So you can write this fi as like this: ai times x to the power of ti plus some lower order terms. So this is the leading term, and this ai is the leading coefficient. So this ai lies within this ring R. So this ring R is Noetherian. And the second thing we need to notice is the degree. So the degree here is di. So these are the only two things we have to play with. First is the coefficient, and second is the degree. Now this ring R is Noetherian, so we know that there is going to be a finitely generated set here, and somehow we want to make this finitely generated set related to these set of polynomials also finitely generated. But we have only two things to play with. One is the coefficients and the second is the degree. So the proof is by contradiction. You take an ideal I in this polynomial ring, and this ideal is not finitely generated. So since we are saying this ideal is not finitely generated, we will reach a contradiction which will then show that Rx is Noetherian, because our assumption of ideal not being finitely generated is wrong. It leads to a contradiction. So ideal has to be finitely generated, which means that Rx is Noetherian. So let us start with this. So we will pick up elements f1, f2, f3, and in a inductive manner, this f1 will have degree d1, just like this fi has degree di. So f1 will have degree d1, so it will be of the form a1 times x to the power of d1 plus some lower order terms. f2 will be of degree d2, f3 will be of degree d3, and the procedure is as follows. So first you set a0 as just the 0. You pick f1, so it is a non-zero polynomial of minimum degree from the ideal I, and from ideal I you just take out the 0 element. Then you construct a new ideal a1 which is generated by this f1 we picked up here. And now we pick up a polynomial f2. This polynomial is of minimum degree in I minus a1, so I minus this ideal. Then we can set an ideal I2 which is generated by both f1 and f2. So now you pick up a polynomial f3 of minimum degree in I minus a2. So these two are not there. So you keep on picking polynomials up inductively. So if ai is f1 f2 all the way to fi, you pick up fi plus 1, a polynomial of minimum degree in I minus ai. So I minus all these polynomials. So now an important remark. So this ideal an is generated by f1 f2 all the way to fn. So it contains elements of degree less than dn plus 1. So because we will pick up fn plus 1, you can look here, instead of I you put in n, fn plus 1 will have degree dn plus 1, which we will pick up from I minus an. So that is I minus all these elements. So if the degree is less than dn plus 1, then it has to be the case that that polynomial is contained within this. So if there is a polynomial f of degree less than dn plus 1, then this f is an element of this ideal. That's precisely the way we have constructed it. So every time we are adding a polynomial into our ideal, and this polynomial in the previous step has been picked up of being the minimum degree in the ideal minus whatever we have before. So this is of degree di plus 1, and this was of degree di. So now we focus on the coefficients of these polynomials. So we have picked up these I polynomials. So let B be the ideal generated by these AIs. So this procedure could go on and on, but you just take an ideal B which is generated by all these coefficients of these polynomials, which we are picking up through this procedure. Now R is Noetherian. So this ideal B which is generated by all these AIs, the leading coefficients of FIs, as you can see here, this is finitely generated. So this B is finitely generated like this. So then we have this an plus 1. This comes from c1 a1 all the way to cn an. Now this an plus 1 is actually lying in polynomial fn plus 1, because now fn plus 1 is of this form: an plus 1 times x to the power of dn plus 1, and then some lower order terms. And by construction, this di is less than or equal to di plus 1. So because every time we pick up a polynomial of minimum degree, so f3 is a polynomial of minimum degree in I minus a2, and the polynomial of lesser degrees, which are fn and f2, have already been picked up. So f3 will have a degree which is more than f1 and f2, otherwise it would have been picked up by now. So construction is like this. So now we construct a new polynomial f, which is fn plus 1 minus the c1 f1 x dn plus 1 minus d1, and so on to cn fn x dn plus 1 minus dn. So we will have now c2 f2 x to the power of dn plus 1 minus d2. So what this does is this cancels the leading term. So let us see this in detail. So f1 is of this form: a1 x d1 plus lower order terms. So now we copy this entire thing right here. So f1 you plug in this a1 x d1 plus some lower order terms. So when you multiply this will cancel out with this a1 comes here. So you get c1 a1 x to the power of dn plus 1 plus some lower order terms. Now you have f2 a2 times x to the power of d2 plus some lower order terms. Now you plug this in here. So this is a2 x d2 plus lower order terms. This will cancel out with this. So you get c2 a2 x dn plus 1 plus lower order terms. So you keep on doing this. So this was the first term, this is the second term right here, plus, and then so on, and then you have the last term corresponding to this. So this we have copied right here. So fn is of the form an x dn plus some lower order terms. So now you can see this. You multiply this in here, an x dn, this will cancel out with this. You're left with cn an x dn plus 1 plus some lower order terms. Now you add all of them. Now if you add all of them, you can immediately see that you will so you are adding this, so on all the way to this. So you see the common term is xtn plus 1, xtn plus 1, xtn plus 1. So you take xtn plus 1 common and you're left with c1a1 plus c2a2 all the way to cnan times x to the power of dn plus 1 and some lower order terms. Now this looks like this because this is precisely an plus 1. As you can see, this is precisely an plus 1. So this thing becomes an plus 1. So you're adding all these things, your leading term is an plus 1 times xtn plus 1. So this is what the leading term you will get. This is the leading term here. So the leading term cancels out. So there is no term of degree dn plus 1 in f. So degree of f is strictly less than dn plus 1. And now we come back to this remark. So if f is of degree less than dn plus 1, it has to lie within an. So it has to lie within an. Now this lies within an, but an is generated by f1, f2 all the way to fn. So this is also lying within an, our ideal an, precisely because it is generated by f1, then f2 all the way to fn. So this lies within an, this lies within an. So it has to be the case that fn plus 1 also lies within an. But this is a contradiction because fn plus 1 is actually lying within ideal I minus this ideal an. So this is a contradiction. So therefore we cannot assume that this ideal I is finitely, that this ideal I is not finitely generated. So it has to be the case that the ideal I is finitely generated, because this assumption leads to a contradiction.